Good evening, guys. I want to give a quick demo of my greatest common denominator algorithm coded in VHDL and programmed onto this board, the Intel DE lit board. Right now, the first thing we'll do is we'll do a reset. Okay, so we reset. That works fine. We'll run through 3 test cases. We'll do 25 and 5. So 25 is should be 5. 5, it's working. Let's do 16 and 2. Should be 2. 2. Let's do 15 and 3. Should be 3. 3. Okay, so it is working. And one thing I do want to talk about is, let's do another one. Okay, 16 is actually what's going inside this code. Like, how is it computing the GCD? So this is my reset signal. It's inverted because by default it's low true, but I inverted it to make it compatible with my code, because as I was testing for a high true. So just to make things easier, I just inverted it. Same with this, the go signal is inverted, so when I press it, one gets outputted. So initially it keeps sensing to make sure that is go 0. If it is 0, it will keep stalling. It will not execute the algorithm. Whenever I press it, go becomes 1, and it goes through all the states that computes the algorithm, that executes the algorithm. Or in a sense, that wires up the algorithm, because in VHDL, we don't want to think about execution. We want to think about wiring, because this is, in a sense, I am making the hardware to compute the GCD. So when I do press it, go becomes 1, and at that done state, it outputs the done signal as 1, and it keeps polling to see if go is 1, if go is pressed. If it is, it will keep outputting done being 1. But as soon as I let go just became 0, and it goes back to its initial waiting state in which done is wired to 0. One thing you might ask, hey, why do you have like the same output in 2 different LEDs? This is because this component has 2 subtractors, but this one has 1 subtractors. And to make up for that 1 loss subtractor, we use 2 muxes. And you might say, okay, how did this play a role in your code? Whenever we're compiling, we could actually see how many logic elements it's being used. Whenever we use 2 subtractor, only 59 logic elements are being used, with 28 registers and 62 pins. The pin stays consistent throughout this process and the register, but the logic element changes. Whenever you take away subtractor and you introduce more muxes, the logic element increases, which is 86. So whenever you have just 1 subtractor and you make up for that loss subtractor by 2 muxes, your logic element increases to 86 from 59. This is completely fine because we have around 50,000 logic elements on this board. But if we want to scale, we definitely do want to think about the effect it will have on a bigger hardware that we want to build. And that was a big takeaway from this lab. Overall, thank you guys, and hopefully I will demo you guys my MIPS processor to keep the tradition going. Have a nice night.